So thank you for joining me to listen my lecture I have on 6.4 Fresnel coefficients. So essentially I will now provide you a means to quantitatively understand how much of light is being reflected and how much of light is being transmitted at an interface of two dielectric media. And of course, along the way, Fresnel coefficients would also give us a means to understand how much of phase changes there might be associated with reflections. So this is what I will be doing here. Essentially in this lecture and then in the follow-up in 6.5, I will be generalizing the math into irradiances and then into reflectivities and transmissivities associated with an interface. So I have now, I want to calculate and I'm really motivated to understand how much of light is being reflected and or transmitted at the interface of the two media. And of course, I want to quantify things so that I would really need to be knowing what is the percentage of light, or what is the portion of light that is being reflected or transmitted. And how do we do here? Light, of course, we do know that we have polarization of light, so that we should also treat things in a general manner, so that we must separate the treatment into the two situations where the incident field either oscillates perpendicular to the incident plane or along the plane of incidence. So essentially, these are two scenarios, two orthogonal incident polarizations, and this is what we must do in order to really be able to describe all possible scenarios with all possible polarization states and so forth. So we start with the former case, and this is highlighted in the figure A, and this is the figure B, the other scenario. So essentially a lot of parameters here. But basically the main thing here to notice is that in the A figure, and this is what we start with, the incident field is essentially oscillating perpendicular to the plane of incidence. And this is now the polarization of light. This is how light is being oscillating, and subsequently, of course, the B field is pointing slightly in a different direction. And now this B scenario that we will be doing after the A scenario is now in this case, the E field would be pointing along the plane of incidence. So essentially the red arrow here is pointing along the plane of incidence, and the B field now would be perpendicular to the plane of incidence. And here, of course, E, this would be the time-dependent polarization, so it would be oscillating quickly with respect to the time. So that this is my point of polarization here. But let's start with the A, and I do not go with the details of all the different parameters. The scenario is still the same. We have two media denoted with I's and T's, and all the parameters associated with it are the same as in the previous lecture. Now, the components that are parallel to the surface, so these would be the tangential components. These, for the E and B fields, are essentially taken from the figure. And what we can say is that these are now, in our case of A figure, we have the case that EI is essentially all that is left. It's always, that's the parallel to the surface, and similarly the reflected field is all parallel to the surface, and all of the transmitted field is parallel to the surface. This does not hold for the magnetic field components, so please look at the A figure in the previous slide and the B field there, so that we note that if we want to take the field component of B that is pointing along the interface, we must take the cosine of theta I to get the component or cosine of theta T to get the right component. So that this is what we have. And now when we are dealing with dielectric media, we are most of the time also able to deal with non-magnetic media. So we can just really safely say that the permeability mu equals to the vacuum permeability mu naught. And these now results in conditions that we can write the continuity equations for the different field components. For the case of E fields, I can write that EI plus ER equals to ET. And then the same thing, the continuity equation for the B fields, I can write now that the minus BI times cosine of theta I plus BR times cosine of theta I must be equal to the minus BT of cosine theta T. And here the latter equation, with the help of the notion that the B field can always be described with respect to the E field's amplitude, so B equals N time divided by C times E. Please remember this from the section 4.2 when we were dealing with Maxwell's equations. And now we have the latter equality turning into also an equality where we have E field components. So that gives me Ni times EI times cosine of theta I minus and plus Ni times Er times cosine of theta I must be equal or is equal to the minus Nt times Et times cosine of theta t. So this is what I got from the continuity equations applied to the magnetic field components. That are the tangential components of the B field should be continuous at the interface of two dielectric media. Now we can solve these two equations, and these result in equations that we solve for the reflected field, and that would give me then two terms, Ni times cosine of theta I minus Nt times cosine of theta, and then at the denominator I have Ni times cosine of theta I plus Nt times cosine theta t, and then I can multiply this with Ei. And similar kind of equation I can find for the transmitted field component Et, and that would be that then on the numerator I have 2 times Ni times cosine of theta I divided with a similar looking term as the denominator. And I multiply this with the Ei2. And these two equations give me possibilities to actually define Fresnel coefficients. So I can really define the Fresnel coefficients, and now I have this perpendicular symbol here, so that I'm considering the E field that is perpendicular to the plane of incidence. So this is why I'm having the perpendicular symbol here. And R is the Fresnel coefficient standing for reflection. And now I can define this Fresnel coefficient that it's essentially the reflected field amplitude divided with the amplitude of the incident field. So this makes sense. It's a very logical choice for defining how much light is being reflected. And now I can plug in the values, and what I have is basically the term that depends on the Ni's and cosines and Nt's like this. So essentially I just take this term and I divide it the both sides with the Ei, and then I can define my reflection coefficient for the case of perpendicular E field with respect to the plane of incidence. And similarly, the T, so that would be the Fresnel transmission coefficient for the case that my incident field is perpendicular to the angle of incidence, plane of incidence, and this is now similarly defined that it's the transmitted field amplitude Et divided with the incident field amplitude. And again, this makes perfect sense, and then I can just look at the above equations and I can see that this is actually the case of this. So what these Fresnel coefficients R and T tell us is that essentially they do tell us how much of incident light is being oscillating perpendicular to the plane of incidence, and how much of that is being reflected and how much of that is being refracted. And please try your best of memorizing this, meaning that why I have this symbol here. So essentially I'm defining now this to the polarization component that is oscillating perpendicular to the plane of incidence. The A figure in the original slide. And now I will do the same thing for the field components that are oscillating along the plane of incidence. So that would be the other orthogonal polarization component of interest. And now the continuity of equations, continuity of field components that are tangential to the interface. So basically pointing along the interface. For the E field components, I get these kind of terms from the figure. And now for the B fields, I get these kind of terms from the figure B. So I'm basically just looking at the tangential components of the fields, and these would be the terms I get out. And now the continuity equations state that the fields are these components are continuous. Then I can turn these different terms into two equations. So basically these turn into Ei times cosine theta I minus Er times cosine theta I must be equal to the Et times cosine of theta t. So I'm just taking these and writing an equality so that the incident and reflected field amplitudes, they must be equal to the Et case so that the continuity would hold. And the same thing, similar case for the B fields like this. And of course, I will do the same magic here that I will transform the B fields amplitude into E fields as in before, and then I can derive the Fresnel coefficient for the case where the E field component is oscillating in the plane of incidence. And that's why I have this sub-label here, so that I have this parallel sign stating that the polarization component now is actually being oscillating in the plane of incidence. And see, as before, I can now define a reflection coefficient to be defined like this. And then we have another kinds of terms here. And please note here that the main difference here is that now I actually have mixed indices. So I have nt here, but cosine theta I here, and ni here, and cosine theta t here, and the same thing here at the denominator nt, but theta I, ni, but theta t here. So this is slightly different from the previous case when the indices were same. And similarly, I can write the transmission coefficient defined exactly in the same manner and looking very similar as in the previous case, but now it's the denominator that is looking different from the case when the field components were perpendicular to the plane of incidence. So what we can now do, we have equations and we can really use them to understand what happens. And let's consider a simple scenario. So let's look at an air glass interface and how things look like there. So I'm in the figure A plotting the reflection coefficient as a function of theta I, the angle of incidence. And I'm plotting the two scenarios. So the reflection coefficient for the case where the field component is oscillating with respect to the normal with respect to the plane of incidence and parallel to the plane of incidence. So this is what happens. And spoiler alert, something interesting seems to be happening here since the reflection coefficient goes to 0 at this specific angle, but more on that later. And now in the B case, I have the air glass, but I'm looking at the transmission coefficients. And I can see that the highest transmission takes place when I'm at the 0 angle of incidence. And interestingly enough, this is actually a good stuff, good for you to look into this trend, so that when I'm increasing the angle of incidence, so I'm approaching so-called crazing angles, the transmission actually goes down. And as you can see here, the reflection goes up similarly. And this is actually quite interesting because in a way, now a simple dielectric medium starts to behave like a mirror. And this is actually quite important because there are scenarios that it would be hard to come up in making mirror materials in given wavelength areas. For example, if you go to shorter and shorter wavelengths to UV light and Röntgen light, it's actually quite hard to make a mirror material there. So here you can see that if you just have a whatever interface that your UV light is shining into, if you actually let the shining to take place at the crazing incidence, so at a very large angle of incidence, most of UV light is being reflected. And I believe like another example would be, for example, the case that you are looking at a smooth surface of a lake. And then when you're looking at the kind of horizon or the island very far away or the nearby coastline, far away coastline, then what happens is that this air-water interface is essentially behaving like a mirror. And that's why you see the beautiful landscape being reflected from the air, because essentially you're looking at things at the grazing angle and the Fresnel reflection coefficient is high. But when you kind of change your perspective and you look down to the water, you still see that the water is behaving as usual, and you can actually see the bottom of the lake nearby your feet. So this is exactly the trend and the kind of physics we can see by just looking at these figures. So even though they may look nothing much to you, when you apply these into real life scenarios and real life engineering problems, we are actually speaking of good stuff here, like really good stuff, I would say. So the coefficients R and T really tell quantitatively what happens, and this is that they tell what happens in terms of the amplitudes. And moments of revelation here, they can be negative in value, as you can see in the A figure. So what this actually means is that there might be a case of phase shift of a pi with respect to the incident and reflected field. So this is the kind of why we have negative values, and this is perfectly fine since we are dealing with amplitudes. If we would be dealing with irradiances, then things would seem a little bit more murky, because how would you define a negative energy? But here it's perfectly fine. The minus sign here just corresponds to the case that there's a phase flip after reflection. Here, this is somehow not as obvious. They can also be larger than unity, and I will just let you to sweat for a while and say that the field is not the same thing as irradiance, and this is what happens here. And this is the kind of what makes it possible that these reflection and transmission coefficients can actually be larger than unity. So they do not, it's the field amplitude that does not yet tell us of the irradiance, but rather we have the refractive indices of the media there in the defining equations. But I think I will be speaking more on that later in the lecture, where I'll be speaking about reflectivity and transmissivity. So when I'm really moving into the irradiance description of reflection and refraction. Now let's finally look further. I want to progress into the Brewster angle. So let's further look what happens for the reflection coefficient R at an air glass interface and for the case where the polarization points along the plane of incidence. So R, that was the equation we had it for it. And now we want to look when this turns into a zero. So basically we want to calculate where that theta p took place or takes place in the A figure of the previous slide. So this coefficient, of course, becomes zero valued when the numerator becomes zero. So that would be the above term here, the top term here. And now when that happens, is that we can then equate that this nt cosine theta t should be equal to ni times cosine of theta. So of course, this equality should hold. And we can now mindlessly at first multiply both sides with sine of theta I. And now we can apply Snell's law so that the equality, we can mindlessly multiply both sides with theta I. And now we can look that I have this ni sine theta here. So I can then apply Snell's law and turn this into nt times sine theta t. And now this latter equality or latter term turns into nt times sine theta t times cosine of theta. And now we can further reduce things. So essentially I can reduce nts since I have them on both sides here. And then I get the equality that sine of theta times cosine of theta I is equal to sine of theta t times cosine of theta t. And now we can find a solution for this equality so that we have a kind of awful looking trigonometric equality, but we can find a condition, maybe not by few trial and errors, but at least with the computer. And now what we can say that this only applies when theta I and theta t are actually complement angles of each other. And this is maybe not very, very transparent for us, but you can verify it by just doing simple numerics. But essentially, this can only hold when theta I plus theta t equals to 90 degrees. And this is how we define what's a complement angle. And now, this incidence angle, theta I, we can define that to be theta p, because it's a very specific incidence angle, and this angle is also known as the Brewster's angle or polarization angle. And where we got started? We got started from the case that we wanted to seek at which incidence angle reflection coefficient goes to zero for a specific polarization component. So what this, for example, says to us that when we have incident unpolarized light, so basically incident light that contains both polarization components. When this kind of light, normal light just from a flash lamp, from an LED arrives to air glass interface. And if it arrives at the Brewster's angle, theta p, this specific polarization component does not reflect at all. So this field component polarized along the plane of incidence is not being reflected at all since the R equals to zero in that case. And that means that all of this component of light actually is being transmitted through the interface. And what this implies to us is that we can actually make polarizers based on the Brewster's angle, so that this is quite nice. And the engineer me is marveling of this case, because we can actually just take a piece of a glass and then we can use that to make a polarization component, a polarizer. And another scenario would be that I would buy a more expensive polarizer that would be, for example, made from calcite, which is by the way, very fragile material, very brittle crystal, so that very easy to break, so that the price would be totally different. So a price of a polarizer based on other physics would be of the orders of several hundreds of euros. And here I can just make a polarizer using a glass plate that costs few tens of cents. So somehow engineering me is marveling of this piece of physics here. And of course, it's a cool, since we are actually looking at the equations we have derived, and we're actually seeing lots of stuff speaking to us from equations. So speaking physics by just taking use of mathematics. So I will rest my case here. So this was my lecture regarding the Fresnel coefficients. And the next lecture, I will be speaking about reflectivity and transmissivity. So essentially, I will be generalizing this description into the irradiances of light. So I thank you for your time, and please enjoy the day. Bye.